All right, so this is our last week of classes. We are going to do two things. We're going to look at chapter on Bitcoin and the Bitcoin architecture that's in your textbook here. So we're going to do that today. I should take like half an hour, 45 minutes if I don't get too distracted. And then we'll give you some rest of the time to kind of keep going on your final project. And Thursday will be all final project sort of stuff. So that'll be our schedule for this. So today we're just going to go through. There's an exercise. There's no lab this week or anything, but there is the one thing you have to turn in this week is this exercise. So there are directions here, just the questions you have to answer, some resource articles you have to find as I'm lecturing today. So as I'm going through this lecture, hopefully you can fill out this exercise stuff. So that's the one thing that's you'll have to do related to today's lecture. And then the other thing will be the final project. And we'll talk a little bit about that again after we go through this stuff. So we kind of skipped over chapter 15 to get to self-driving cars, a couple of things. And I just want to jump back to chapter 15, where we talk about blockchain and Bitcoin mining. I think it's important to talk about blockchain technology somewhere. We don't have it anywhere else in our curriculum, so that's why I liked that it was in here. Blockchain is one of those technologies that in the last 10 years has been kind of going up and down. People are interested in it or not. And it's somewhat related to interest in Bitcoin and other cryptocurrencies and how much interest or how much, what kind of problems there are with this. But the technology is rather interesting. So we're going to try to look at this somewhat from a technology point of view here, because blockchain can be used to make a cryptographic currency, but it can be used in a lot of other ways. I see companies doing research or working on ways to put medical records in a blockchain or store other information or data in a blockchain, inventory systems to track like inventory from farmer's field to your dinner table. You could track and see how produce or other food is combined and moved around through using a blockchain technology and stuff like that. So it's an interesting technology that can be applied to different things besides just this sort of digital currency sort of idea. But a lot of times blockchains now are used to track cryptographic currency, cryptocurrency, or digital currencies here. And they use a digital wallet here. Digital wallet is something that maintains your balance of this. It is always not that different than like if you have an Apple wallet, or I have a Google wallet on my phone. I have credit cards tied to that, and I can pay and stuff for that. I don't necessarily have a balance. Those are just more like access to your credit cards or that sort of stuff. Where this is more like maybe electronic bank or something where you could have a balance in there. There's a couple types of digital wallets here. One is what is called a hardware wallet, and this is where the information is stored on a physical device, often like a USB drive sort of device, and your keys for your digital currency are stored right on that hardware device, like you'd have a flash drive that's set up to be like that. Another way is what are called software wallets, and these are out there, and you can store information on them, often on your phone. and then you could access and do stuff with them. And again, that's where I think it's similar to like a Apple Wallet or a Google Wallet here. I have mixed feelings about the whole cryptocurrency or digital currency stuff. I do, own a little, I've played with this. I put a little money in there just to see what it's like and stuff like that. So I have two different software wallets that are on my phone that are interesting. But so I have explored this area just a little bit. Exchange wallets, there are places where you can trade information and stuff like that. Let's see. So like Binance is one of those areas, and again, they can there'll be a website that you can buy, sell, and work with Bitcoin or other currencies. And it also shows you like this phone app where you can again do the same sort of stuff. This is an exchange that lets you buy and sell and work with it. And so you can have a wallet on this exchange also. So those are kind of the three types of wallets that are out there. Let's talk about what a blockchain is actually here. So all a blockchain is what we call a ledger, a shared ledger of transactions that we have. So we break these transactions. We have a whole bunch of transactions. We break them up into blocks, put a whole bunch of them together in one block. So you'll have this block here that's made up of a bunch of transactions here. So every time someone does something with a Bitcoin or some Bitcoins, if this is a Bitcoin blockchain, you would see a transaction here to here, here to here. They're identifying from every digital wallet to another digital wallet that this data is moved from. So every transaction is recorded in here. The blocks have, we have to make sure that they are kept secure and not changed. And so we use something called a hash for that. And so a hash is just, I don't remember this, I think we talked about this in the CS principles class, where for error correction, if you're going to take a bunch of data, you can calculate some number. Maybe you add up all the bytes, all the bits in that chunk of data, and then if it's odd or even, you encode that as a parity bit. That's a simple kind of idea of a hash. But we want to make it so if you change anything in that chunk of bits, that it will be recorded in the hash. The hash will be different. So we do some much more complicated calculations on the bits, so that a hash is just some numeric value that kind of represents that data, in that if you change the data in any way, the hash number will change also. So we calculate the hash. We have all these bits. We calculate the hash of this and make sure. You might see this sometimes when you're downloading data files from the internet. They might have some hash numbers or some other numbers like that that'll go with them. They'll tell you, so you can verify once you downloaded the data that it is accurate and no one has gone in and changed that. So if you're downloading some software, sometimes that has hashes in it also. So this just shows us, now we chain these blocks together. That's why I call it a blockchain. So when we add a new block, it has the hash for the previous block embedded in it. And the hash of that block includes the hash of the previous block. So then if you even change a previous block, that will change all the blocks going forward, because all of them will have incorrect hashes going forward for this. So that's kind of the setup here for this. Now there's a special part of this. There's a timestamp, and there's also this nonce area, and this is just a kind of blank area in the block where we can kind of, you can think of it as a null area where we're not using it, but we can put whatever data we want in there. And we're going to try to manipulate this data in this nonce so that it generates interesting hash values for us here. And so we can talk a little bit about that and what this nonce does. So again, here's what the textbook says. Zoom in a little bit more on this. So when we're kind of creating a new block, we have people who will try to figure out the hash, calculate the hash on all of this here. And so what we'll try to do is we want a particular type of hash. So we'll try a nonce. Maybe we'll try all zeros in the nonce, and then we'll calculate the hash. And then we'll try another a nonce with some ones in it and calculate the hash. And we'll keep calculating the hash with different random nonces or different nonces in here until we get a certain type of hash there. One way I think of it is like the hash is a whole bunch of binary digits, and we want maybe the first 10 of them to all be zeros for this. So every time we change one bit in here, we get a new hash. So we can change a bit. But again, we don't want to change a bit in the transactions. That would be bad. We can't change a bit in the previous hash. We probably don't want to change this timestamp, although that's a little up in the air. But there's this whole area, this area called the nonce, where we can change bits. So we can randomly change bits there. We'll just keep randomly changing bits there and calculating hashes until we find a nonce that generates a really good hash. And it's really just random tries. There's no algorithm. The whole thing is set up so there's no good algorithm to help us do this other than trial and error for this work. So that's what the nonce is kind of set at for this. We use pretty big blocks in an algorithm called SHA 256 for this. And this is a special encryption algorithm. It's the same algorithm that encrypts a lot of the internet there. So when you are sending a web page and stuff, a lot of it uses this sort of kind of here. And so it creates a 256 bit hash value. So it just is a description of how you calculate a hash value for this. And it's set up so that changing any part of the data block, even a single bit, will result in a completely different number hash value. So it's independent of the size of the block, and computing it, you can always generate the same hash. If you have some data, you can follow this algorithm, it always gives you the same hash. But it's really hard to tell you what that hash is for this. So here's how we go about computing this hash. We break our block into chunks of 512 bits here. And we need it to be 512 bits. So if it's not, if it's less than that, we do some padding. We append a 1 to the message, and then we append the number of zeros to the message so that the length of the message is 64 bits less than a multiple of 512. Oh yeah, I said it had to be 512. It has to be a multiple of 512. So, 512, 10, 24, 20, 2048, any of those multiples, powers of 2, basically. So once we have that, we do this, we append a 1 after the message, we then append some zeros so that we just have 64 bits less left, and then we add our hash here. The length of the bits in the original message is put in here, and then we calculate the hash based on that. So this is like an example of a hash output for us. I don't know if the textbook does a great example explaining this, and so I'm going to jump to this video. I really like the visualization videos from this website creator, 3 Blues, 1 Brown. They do some amazing math videos and stuff like that. So I'm just going to show you that video here for this. How are we doing on sound?
Of Bitcoin. Many people have heard of Bitcoin, but it's a fully digital currency with no government to issue it, and that no banks need to manage accounts and verify transactions. And also that no one really knows who invented it. And yet many people don't know the answer to this question, at least not in full. Instead, and to make sure that the technical details underlying the answer actually feel motivated, what we're going to do is walk through step by step how you might have invented your own version of Bitcoin. We'll start with you keeping track of payments with your friends using a communal ledger. And then as you start to trust your friends and the world around you less and less, and if you're clever enough to bring in a few ideas from cryptography to help circumvent the need for trust, what you end up with is what's called a cryptocurrency. You see, Bitcoin is just the first implemented example of a cryptocurrency. And now there are thousands more on exchanges with traditional currencies. Walking the path of inventing your own can help to set the foundations for understanding some of the more recent players in the game and recognizing when and why there's room for different design choices. In fact, one of the reasons I chose this topic is that in the last year, there's been a huge amount of attention and investment and, well, honestly, hype directed at these currencies. And I'm not going to comment or speculate on the current or future exchange rates, but I think we all agree that anyone looking to buy a cryptocurrency should really know what it is. And I don't just mean in terms of analogies with vague connections to gold mining. I mean an actual direct description of what the computers are doing when we sell and receive and create cryptocurrency. One thing worth stressing, by the way, is that even though you and I are going to dig into the details here, and that takes meaningful time, you don't actually need to know those details if you just want to change the cryptocurrency. Just like you don't need to know the details of what happens under the hood when you swipe a credit card. Like any digital payment, there's lots of user-friendly applications that let you just send and receive the.
Yeah, I'm going to jump around. This is a long video, so I'm just going to jump to a couple sections here.
Without Alice, how are we supposed to?
So here he's trying to do a ledger. Like if you have 3 friends and you're out a lot and you want to exchange money a lot, how do you keep track of who owns what? And maybe you just Venmo each other money back and forth, something like that. So this is just the idea of how would we create our own version of that.
All what the sender meant. Well, this is where the first bit of cryptography comes in. Digital signatures. Like handwritten signatures, the idea here is that Alice should be able to add something next to that transaction that proves that she has seen it and that she's approved of it. And it should be infeasible for anyone else to forge that signature. At first, it might seem like a digital signature shouldn't even be possible. I mean, whatever data makes up that signature can just be read and copied by a computer. So how do you prevent forgeries? Well, the way this works is that everyone generates what's called a public key private key pair, each of which looks like some string of bits. The private key is sometimes also called a secret key, so that we can abbreviate it as SK by abbreviating the public key as PK. Now, as the name suggests, this secret key is something you want to keep for yourself. In the real world, your handwritten signature looks the same no matter what document you send. But a digital signature is actually much stronger because it changes for different messages. It looks like some string of ones and zeros, commonly something like 256 bits, and altering the message even slightly completely changes what the signature on that message would look like. Speaking a little more formally, producing a signature involves a function that depends both on the message itself and on your private key. The private key ensures that only you can produce that signature, and the fact that it depends on the message means that no one can just copy one of your signatures and then forge it on another message. Hand in hand with this is a second function used to verify that a signature is valid. And this is where the public key comes in. All it does is output true or false to indicate that this was a signature produced by the private key associated with the public key that you're using for verification. I won't go into the details of how exactly both these functions work, but the idea is that it should be completely infeasible to find a valid signature if you don't know the secret key. Specifically, there's no strategy better than just guessing and checking random signatures, which you can check using the public key that everyone knows. Now think about how many signatures there are with a length of 256 bits. That's 2 to the power of 256. This is a stupidly large number. To call it astronomically large would be giving way too much credit to astronomy. In fact, I made a supplemental video devoted just to illustrating what a huge number this is. Right here, let's just say that when you verify that a signature against a given message is valid, you can feel extremely confident that the only way someone could have produced it is if they knew the secret key associated with the public key you used for verification. Now, making sure that people sign transactions on the ledger is pretty good, but there's one slight loophole. If Alice signs a transaction like Alice pays Bob $100, even though Bob can't forge Alice's signature on a new message, he could just copy that same line as many times as he wants. I mean, that message signature combination remains valid. To get around this, what we do is make it so that when you sign a transaction, the message has to also include some sort of unique ID associated with that transaction. That way, if Alice pays Bob $100 multiple times, each one of those lines on the ledger requires a completely new signature. Okay, great. Digital signatures remove a huge aspect of trust in this initial protocol. But even still, if you were to really do this, you would be relying on an other system of sorts. Namely, you're trusting that everyone will actually follow through and settle up in cash at the end of each month. What if, for example, Charlie racks up thousands of dollars in debt and just refuses to show up? The only real reason to revert back to cash to settle up is if some people, I'm looking at you, Charlie, owe a lot of money. So maybe you have a clever idea that you don't actually have to.
I'm gonna jump ahead to the next part, talking about how, once we have these digital signatures, how we could separate these or work on a ledger for
Like
these.
a website where anyone can have new lines. But that would require trusting a central location, namely who hosts the website, who controls the rules of adding new lines. To remove that bit of trust, you'll have everybody keep their own copy of the ledger. Then when you want to make a transaction, like Alice pays Bob $100 ledger, what you do is broadcast that out into the world for people to hear and to record on their own private ledgers. But unless you do something more, this system is absurdly bad. How could you get everyone to agree on what the right ledger is? When Bob receives a transaction, like Alice pays Bob $10 ledger, how can you be sure that everyone else received and believes that same transaction? That he'll be able to later on go to Charlie and use those same $10 ledger to make a transaction. Really, imagine yourself just listening to transactions being broadcast. How can you be sure that everyone else is recording the same transactions and in the same order? This is really the heart of the issue. This is an interesting puzzle. Can you come up with a protocol for how to accept or reject transactions and in what order, so that you can feel confident that anyone else in the world who's following that same protocol has a personal ledger that looks the same as yours? This is the problem addressed in the original Bitcoin case. High level, the solution that Bitcoin offers is to trust whichever ledger has the most computational work for interest. I'll take a moment to explain exactly what that means. It involves this thing called a cryptographic hash function. The general idea that we're built to is that if you use computational work as a basis for what to trust, you can make it so that fraudulent transactions and conflicting ledgers would require an infeasible amount of computation to bring about. Again, I'll remind you that this is getting well into the weeds beyond what anyone would need to know just to use currency ledgers. But it's a really cool idea, and if you understand it, you understand the heart of Bitcoin and of other cryptocurrencies. So first things first, what's a hash function? The inputs for one of these functions can be any kind of message or byte. It really doesn't matter. And the output is a string of bits with some kind of fixed length, like 256 bits. This output is called the hash or the digest of the message. And the intent is that it looks random. It's not random. It always gives the same output to a given input. But the idea is that if you slightly change the input, maybe editing just one of the characters, the resulting hash changes completely. In fact, for the hash function that I'm showing here, called SHA-256, the way the output changes as you slightly change that input is entirely unpredictable. You see, this is not just any hash function. It's a cryptographic hash function. That means it's infeasible to compute in the reverse direction. If I show you some string of ones and zeros and ask you to find an input so that the SHA-256 hash of that input gives this exact string of bits, you will have no better method to just guess and check. And again, if you want to feel for how much computation would be needed to go through 2 to the 256 guesses, let's take a look at the supplement video. I actually had one for much fun that back there. You might think that if you just really dig into the details of how exactly this function works, you could reverse engineer the appropriate input without having to guess and check. But no one has ever figured out a way to do that. Interestingly, there's no cold, hard, rigorous proof that it's hard to compute in the reverse direction. And yet, a huge amount of modern security depends on cryptographic hash functions and the idea that they have this property. If you were to look at what algorithms underlie the secure connection that your browser is making with YouTube right now, or that it makes with your bank, you will likely see the name SHA-256 show up in this. But right now, our focus will just be on how such a function can prove that a particular list of transactions is associated with a large amount of computational effort. Imagine someone shows you a list of transactions, and they say, hey, I found a special number, so that when you put that number at the end of this list of transactions and apply SHA-256 to the entire thing, the first 30 bits of that output are all zeros. How hard do you think it was for them to find that number?
So this is kind of the heart of Bitcoin, what we call Bitcoin mining here, is you have a ledger of transactions, and then you have this number, this annoyance, that you can put in here, and you can put any random number you want in there. And then you want to generate a hash function for it here. And then the hash function has, in like this case, some requirement. In this case, he's just saying it starts with 30 zeros. And that if you want to do this, this requires a lot of work. You have to try out lots of examples. You might randomly get one right, but in general, you won't. Like, you won't randomly win the lottery. You have to try it a lot of times. So it's a proof of work here. So this is what's an important part of this whole process.
The probability that a hash happens to start with 30 successive zeros is 1 in 2 to the 30, which is about 1 in a billion. And because SHA-256 is a cryptographic hash function, the only way to find a special number like that is just guessing and checking. So this person almost certainly had to go through about 1 billion different numbers before finding their special number. And once you know that number, it's really quick to verify. You just run the hash and see that there are 30 zeros. So in other words, you can verify that they went through a large amount of work, but without having to go through that same method yourself.
Okay, I'm going to stop this here. The whole videos you can watch later. But that's what this hash function is. So a hash function, again, we calculate a number based on some data, some bits here. And we talked about how the textbook talks about how you pad this number here. You append a bit to the message. You then put some zeros in there. So there's some methods you do some padding here. And then this is this integer you can put in here that you can, and that's the integer you want to put in there to make some special hash function here. So again, Bitcoin mining is when you just do some of these computations. You're given a bunch of transactions that'll be in a block, and you want to compute figure out what random number you can put in there so that the hash fits some criteria, like has a 30 zeros at the beginning of it for that. So And you just have to try there's no way, no algorithms other than to randomly try lots of numbers in here for this. Now, if you find a combination, and you can just find it by luck, but then you get a reward. And we can actually look at how often these blocks are generated here. So the last block was generated 7 minutes ago for this. And this is the length, this is the hash of that block here. And someone, calculated this hash, and you can see there's a bunch of zeros. They found a hash with a bunch of zeros at the beginning of it here for that block. Now, they'll be given a reward for this. The reward comes from two places. One is you pay a small fee for these transactions. So every one of these 4,000 transactions is paying a small fee. And also, as far as the Bitcoin protocol, you get a small reward of Bitcoin when you find one of these hash ones. And that's what's kind of called mining. You try out random numbers, you find the magic, a magic number, or a good number that does this hash, and then you're rewarded with some Bitcoin. And so, like this last Bitcoin, they received 3 Bitcoin, or about $180,000 for finding this combination. So anyone who can find these combinations is really good. Really useful. So you're thinking, geez, I have a computer, I should be doing this work here. So let's look at that. I'm going to go back to the textbook here. So there's software you can get for mining Bitcoin. You just have to find this stuff. How hard can it be? There are these pools where people get together, but then you have to share the reward with a bunch of people. Who wants to do this? I'm just going to do it on my own CPU, right? So you can set up your own CPU here, and you can be doing some mining here. Now, it's hard to calculate, because it's random. You could find it in the first day or two there, but on average, it will take you about 130 billion years to find that. So you have to pay your electricity bill on your computer and time for 100 billion years to get your $100,000 payout. So maybe not that great, but they're thinking, oh, but I've got a gaming computer, GPU, I can go really fast. So on my GPU, I can run it, and you go a lot faster there. It only takes 1 times 10 to the 12th minutes, barely any time at all. So it only takes about 2.6 million years, not billion years. You're 1,000 times faster. It's only going to take 1 million years for you to find a Bitcoin solution there. Now, it used to be a lot easier to mine Bitcoin, but now it's a lot harder for things. So again, it's going to take you billions of years with a CPU, millions of years with a GPU. And I think it gets harder there. And that kind of idea is that, let's say we have to find a hash with that starts with 30 zeros in it for that. Well, originally, like a year ago, maybe we only had to find a hash with 15 zeros in it, or less. So it started off where finding these hash values was a lot easier there. And we used to be able to mine, you could mine Bitcoins on a GPU and actually have a good chance of finding some and things like that here. But the Bitcoin stuff is set up for every 4 years. There's what's called a halving, where the amount of reward and the difficulty increases on this. So we just had a halving in Bitcoin, I don't know, a week or two ago. I don't know. And so it made it harder, and you got less reward for this. So So I said it used to be easier. So if you were a computer student 10 years ago and you did have a computer, but there was a computer up in the computer club room that had a good GPU, you might download software and run it on there, and you weren't paying electricity because it's college computer there. So you might run that computer 24/7 mining Bitcoin for a while. So one of the former computer club presidents emailed me about 2 months ago and said, hey, by the way, do you still have any hard drives from our computer club from about 2011, 2012? Because we may have been running a Bitcoin mining up in the computer lab upstairs for a while. And we're just thinking it might be worth checking on those now. So it's a hard. So I have a couple hard drives from back then that I'm trying to look at and explore. So there might be a digital wallet file on this hard drive, and there might be a couple Bitcoin on this file, according to our computer alumni. So I looked on one that I thought was real promising. It was from 2013. There was a Windows drive, so I just plugged it into my computer and searched for the digital wallet, and I didn't find it. But I can't remember, but I'm pretty sure that the main computer we ran back then was a Linux box, and they had a shared Linux stuff. So I have a couple of drives that I can't read them on Windows because they're Linux. So this summer I'll see if I have a chance. And so this is one of them. Also, this is an old one. This doesn't have a SATA cable, so I can't plug it in. I have to plug it in. This is the older cabling system. I have to plug it in a little differently to get to read on my computers. So so that's our lost Bitcoin. And again, the textbook says it's estimated 4 million Bitcoin have been permanently lost by their owners because they've lost access to their keys here. So your job is to look at in January 2012, what was the price of Bitcoin? What was it worth, and what is it worth now? And if we have 2 Bitcoin on this hard drive, how much is this hard drive currently worth for us? So, and I'll let you know if I ever find any Bitcoin. Or you just come and I retired and you go, where's Tom? And goes, oh, he bought an island in the Bahamas, then you'll know I found the Bitcoin. So, Bitcoin, they talked about this proof of work. Again, it's this calculation and again, it takes a lot of computation to do it. The book goes over a lot of detail on how you can mine stuff here. Different hardware setups you can use in different types of circuits, special boards you can buy just for mining Bitcoin, and then how much you have to pay for electricity for this sort of stuff, and the whole feasibility. But this whole idea is tied into this proof of work, and that you have to do a lot of computational work to earn Bitcoin and to resolve the blocks. Just to keep Bitcoin running requires a lot of energy, and there's a lot of question about, is that environmentally secure or justifiable? So I want you to find an article that talks about the environmental impacts of Bitcoin mining and puts that in here. So now there are some other alternatives to Bitcoin. Well, there are a lot of alternatives. One of the things I talk about in this example is that you can just create your own cryptocurrency once you know the rules. And this is all done in software, and it's all stored on GitHub. And you can just clone, fork GitHub versions, and you can just copy it and make your own currency here. And so a lot of people have done that. And so a lot of people make their own currency, sell it, and then just, it's not working, and just, hype it up. And then, and just leave and just say, take on, and it might not be on a centralized server, it might not be good. There's a lot of scams. It's a very easy way to scam people. You can create your own kind of stuff. And so there's not very many regulations with these cryptographic currencies, and so there's a lot of people taking advantage of these, and now we actually do see a couple people going to jail as a result of this sort of stuff, because they've con people out of hundreds of millions of dollars and things like that. But there are, there are some also very legitimate uses of it. I'm going to just talk about Ethereum a little bit. There's a couple articles here. No, we don't. I've been doing a lot of searching for lots of laser cut files and CNC files. So all my ads on YouTube are for CNC laser cutting machines and stuff like that.
When in blockchain interchangeably, by the end of this video, we will understand the key difference.
So this walks through Ethereum, and Casey will go through this sort of stuff, explain what Ethereum is and how it's set up. Again, I'm not going to watch this, but you're free to watch this if you want to learn more about it. Ethereum, I'm going to click on this article by the Wilson. Oops, I'm going to open up that in another layer, I guess. Okay, so this is from the Wilson Center, which is a government-funded research organization, and it talks about Ethereum and how it works. Ethereum is set up similar to Bitcoin. It's a blockchain, but besides just putting transactions on the blockchain, you can put data, and in fact, a particular type of data is called a smart contract. So you can take code, you can write code and put that on the Ethereum blockchain, and then other people can run that code as a smart contract. And so there's a fair amount of sophistication on some Ethereum and some of these other blockchains as far as not just storing transactions, but storing code and what we call smart contracts on here. Ethereum used to work on this proof of work concept, which similar to what we see with Bitcoin, but has since 2022, for the last couple of years, has moved to what is called a proof of stake here. So that has made it a lot faster and easier to figure out, to approve blocks on the blockchain. Question is, well, how can you keep fraudulent blocks off of the blockchain? And the way they use it is what is called proof of stake. You can stake or reserve your your Ethereum in a special way, and then the people with those reserves vote on transactions, and winning transactions get voted on and approved there. It's of course pretty complicated, but again, it doesn't require all this computation and works very fast. Ethereum also still is slow compared to like Visa transactions, credit card transactions. So there's this whole area of where we can have these what are called layer 2 solutions, or places where they'll do a bunch of transactions on a different layer of Ethereum, roll up the transaction and say, send one big transaction to Ethereum to get approved. And so there's ways of rolling up these transactions to speed up things. So again, Ethereum has these smart contracts where you can you can write code and put it on the blockchain, and others can then run your code. So you have this whole ecosystem of stuff. It works out proof of stake. And again, we have these layer 2 solutions here. And that allows us to create things, roll up transactions to make things a lot faster on this. So, questions on cryptocurrency, Bitcoin? I'll just warn you, there's a lot of hype on there, so if your interest is piqued, be careful, because there's a whole bunch of videos that are going to try to make you rich, very quickly, because everyone gets rich. Anyone who even does anything in crypto just gets rich. That's what a lot of these videos, and there's a whole ecosystem talking about this, all these scams, all these different currencies and all this stuff, and this way of taking new people, building up their excitement into cryptocurrency and then taking their money from them. So just be warned that it's a very easy place to lose some money there. There's legitimate, again, it's not very much regulated. So again, there's very much legitimate areas of this area, but there's also a whole area that's not legitimate out there. So be careful if you want to do anything in that realm for that. So I find the whole technology really interesting. That's why I have a couple digital wallets. I don't have a Bitcoin, but I have some small little fraction of a Bitcoin and a couple things like that. So, all right. So this week you just have to do that, do the exercise, and then the next thing is we're trying to wrap up the final phase of our project here. So we will demonstrate our project at the CIS showcase. That'll be this coming Monday, the first Monday of finals here, and it'll be at 4 o'clock. It'll be in this lab and the other lab. Generally, what you'll do is come here, set up your Raspberry Pi or something like that if you have something to set up, and have a short presentation, something you can put on the screen that'll explain your project. And then people will wander around and ask you about your project there. So other teachers will, other students will. So there's no formal presentation. You don't get up here and you don't present. You just have to be there, and then you'll get to walk around and see one of my game design students are still working on animating this dragon and the dragon attack stuff. And so we'll see if the dragon is flying and attacking by Monday. They had it kind of flying today, so we keep our fingers crossed on the flying dragon for that. So yeah, there'll be some games to play there and other things to try out at the showcase. If you can't do the showcase, you can record a short video and submit that of this. So questions on the showcase, stuff like that? And we'll have pizza at the showcase as always. I think, were you most of you at the showcase in the fall? You weren't at the showcase in the fall? A bunch of you, some of you were. So it's a lot of fun. So we try to set up a somewhat low stress. I mean, final weeks are stressed enough. So, right. Okay. So we'll wrap up here. And again, if you want to work on your project,